Section 5.3 is talking about annuities, future value, and sinking funds. So in sections 5.1 and 5.2, we only looked at lump sum payments. So 5.3 and 5.4 will involve periodic payments, where you're making payments at some regular intervals. In 5.3, we'll be talking about putting payments into an account, and in 5.4, it will be money being paid out of an account. So an annuity is just a sequence of equal payments made at equal periods of time, and the time between the payments is called the payment period. So that's often annual or semi-annual or quarterly or monthly, just as the interest compounding formulas were. So the time from the beginning of the first payment period to the end of the last period is called the term of the annuity. So if this is year one, this is a timeline, and year two, and so on to the last year, then the term of the annuity is this entire time period. And annuities are used in two ways. They're used to accumulate funds, so that's this section 5.3, but they're always also used to pay out funds, and that will be section 5.4. So in this section, money is going to be being paid into an account on a regular basis, and then we are going to be looking at what is the future value of all those deposits. Well, each deposit is in the account for a different amount of time, so it's a little more complex than section 5.2, but we'll have formulas where somebody else has already figured out how to figure out the value, even though the amounts of money have been in the account for different time periods. So the simplest is called the ordinary annuity, and notice that the word ordinary with annuity always talks about the payment being made at the end of the period. So the frequency of the payments is the same as the frequency of compounding the interest, and those two things together are what make it an ordinary annuity. So if you're putting $1,500 in every 6 years into an account, paying 8% interest compounded annually, this chart shows how the money gets interest compounded. So at the end of year one, the first amount of $1,500 goes in. Well, it's going to be compounded 1, 2, 3, 4, 5 times. So there's an exponent of 5 on the compound interest amount. That's the exponent that says compound this 5 times. So the next amount that goes in, it's 1,500 again, but now it goes in at the end of year 2, so it only gets compounded 1, 2, 3, 4 times. So its exponent is 4. And so on for the next 1,500 and the next 1,500. Well, there's a formula, an algebraic formula for how do you add these numbers together. So we don't have to worry about how you get to the formula. We just get to use the formula. So because there's a pattern there, you can come up with a mathematical formula. And this is the formula. It says if you want to find the future value for some regular payment amount made at the end of each period, this is the formula you use. And the I and the N are exactly the same as they were for the compound interest in the previous section. So let's look at this example where we have $1,500. So we're looking for the future value of $1,500 deposited at the end of each year. So I'm going to have 1 plus, then my interest rate is 8%. So when I change that into a decimal, it's 0.08. Then you would divide by the number of times you compound each year, but that's a 1 in this case, but I'm going to show it here just so you know I didn't forget. And then the number of times you compound is once each year for 6 years, so that's going to be a 6. Then from that quantity you subtract a 1 and divide by always the same interest rate. So the same interest rate's always in the top and the bottom of these equations, make sure it's identical in the two places. So do this on your calculator and you should get $11,003.89. And let me know if you have any issues with getting your calculator to give you that result. And the Math Center can also be very helpful with just using your calculator. Okay, so then I have another example here, and I just typed the formula again so that you could have it conveniently close by while you do this calculation. So let's do the future value of a payment amount of $500, 1 plus, my interest rate is 1%, so that's 0.01 as a decimal. And now we're doing quarterly compounding and quarterly payments. So I need to divide by 4 because I'm doing it 4 times each year. Then quarterly for 3 years is 4 times each year for 3 years, so that's an exponent of 12. Then I need to subtract the 1 and then divide by 0.01 over 4. And then with some calculator magic, you should get 6,083.19. Okay, so the next example is a more complicated scenario that I don't think the book explains very well, so let me try to explain it better. This first annuity is $500 a month, 5% compounded monthly for 20 years. Then they don't say this explicitly in the problem, but then this future amount gets rolled into the second account and is subject to the situation of the second account where it's 8% interest compounded monthly for 20 years. And then there's a second annuity that's $1,000 more a month being put into that second account. So there's 3 pieces. The first annuity, then that money gets set into an account with interest compounded monthly, and then there's a second annuity. Okay, so let's do them one at a time. So first we want to know what's the future value of the $500 annuity, and we have 1 plus interest rate of 5%, so that's a decimal of 0.05, compounded monthly, so divide by 12. Monthly for 20 years means you're going to compound 240 times. Then you subtract 1 and divide by always that same interest rate, so 0.05 over 12. And this gives you 205,516.83. So that's the value of the first annuity. Then this gets deposited in the second account. So we take this amount, the 205,516.83, and we just do compound interest with the second account's information. So it's invested at 8%, 0.08 as a decimal, monthly, so divide by 12. Then monthly for 20 years is 240 times it gets compounded. So for that amount, I'm getting 101254091. So that's the amount of the first annuity, after it gets put into the second account to sit while the second annuity is being formed. Okay, now we have the second annuity, which is the $1,000 a month. So we want the future value of the second annuity. This is the second annuity. So we have a payment of $1,000 a month. 1 plus my interest rate of 8% is a decimal of 0.08. Monthly divided by 12. Monthly for 20 years is 240 compoundings. Subtract 1 divided by that same interest rate. And this is going to be the amount in the second annuity. So for that one, I'm getting 589,020.42. And I always like to double check. Yep. So then your final answer you're going to add this amount and this amount together, and you get 1,601,561.32. So that's your final answer. Okay, then another way annuities are used is rather than solving for the future value, if you know the future value you want to accumulate, you can figure out what payment amount does that mean you need to make to come up with a certain amount at the end, if you're doing it like an annuity where you're putting the money at the end of periods. So let's set it up like the annuity calculation, but say I want a future value of 65,000 and I want to solve for what my payment should be. So I'm going to fill in all my numbers. Interest rate of 6%, so that's 0.06 as a decimal. Semi-annually, so divide by 2. Semi-annually, twice a year for 4.5 years. That means I compound 9 times. Minus 1, and then always divide by the same interest rate. So now what I would do is calculate the amount in this square brackets, and I would do that on my calculator, and then I would do 65,000 divided by answer. So if you do the part in the square brackets first, your calculator will remember that amount. And then when you type in 65,000 divided by answer, it will divide by that number. Or you can rewrite the whole equation and write this underneath the 65,000, but it's a lot of writing. And I like the idea of let's just keep writing the equation the same way and then manipulate it to solve for the thing that we're asked about. So if you do this calculation, you should come up with 6398.20. So this is the amount of payments that should be made semi-annually for 4.5 years, so that you will have accumulated $65,000 at the end of the time period. Okay, so I'm going to pause here and do another video for the last part.